Okay, we're gonna talk about CSE 384 this time. It's of course about AI. Think like your classical AI, not like ChatGPT. So we talk about like classical AI algorithms that aren't isn't really machine learning, but still technically considered AI. And you'll find out that like guys, AI isn't all that, okay? It's just a computer, and it does computer things, okay? So we're gonna start it off by talking about space search. So like the name suggests, we're searching through a space of states. So the first thing to talk about is what is the point of doing this? So when we do this, we're kind of like interested in finding um, solutions to specific kind of problems that can be modeled by like these state spaces. So for example, like we gave you how like mazes and stuff. Like, those like classic mazes that you find in those kids. Yeah, like if you guys ever went to like a restaurant and then like they have like those things for kids, like the coloring, or like the maze, crossword or something like that. Like those kids puzzles at the restaurant. Yeah, those mazes. Um, that is technically you could formulate that as a state space search problem. Um, where like you're trying to search for like the solution to the maze, right? Like the path that gets you out of the maze. So, um, yeah, and so it makes sense now to talk about what a state space is. So, state space it holds a bunch of stuff. So not that much, but first of all, you have to have a set of states, which is pretty much like the nodes of your graph. I'll explain that later, but let's keep using the maze example. So your states in the maze example would be kind of like it would be the actual maze itself, like the layout of the maze, and then it would be where you're standing right now in the maze. So pretty much the state represents your current your current status, like where you are in the maze. Okay, that's what a state is, and you and when you're searching for stuff like a specific state, then that means that we need to define which state we're searching for. So in the case of our maze problem, we're going to be searching for um, the exit, right? So that's like the layout of the maze, and then our position would be in front of the exit square, and in the state space we call that a goal state. Um, and we could have multiple goal states. Like in your maze, you could have like multiple exits. Like usually there's only one, but you could include more if you wanted to. Okay. All right. And if you have a goal state, it also makes sense to define where you start. So that's your initial state. That's like you at the entrance of the maze. And last thing is you need to be able to define a way to move between your states. So a transition function that pretty much takes one state and then it tells you where you can go. So like for example, at any given point, like location in the maze, like maybe I can like move in four directions, like up, down, left, right. But then like sometimes there's like a wall, right? So I can only move in specific directions. And if I move in another direction that's free, then now I'm in another state because I changed conditions. So that's what a state space is. And if you know anything about like algorithms, like in computer programming, then finding a solution to a maze problem feels a lot like DFS. And that's exactly what we're gonna talk about first. So there are a bunch of different algorithms for state space searching. We talk about some of them in this video. I'm probably gonna talk about 3 different ones. So we'll talk about EFS, BFS, and then we'll talk about kind of like why they're not that great. And then we'll talk about the fix to them. But then, even then, this fix is kind of ass. So there are other ways to kind of like make it better, which we'll talk about next time. Okay. So let's talk about DFS. And now from now on, we're gonna try to move away from the main example. And now, we're gonna try to interpret our state space as like a tree. So now our DF is gonna traverse a tree. And this tree can potentially have infinite depth. So it can go infinitely. Which is really tricky to think about because usually you don't have something like that. But it can potentially have infinite depth. And we also, on this tree, we also define something called a branching factor, which pretty much is like the average number of children that a tree node has. This is important because the branching factor comes up when we're analyzing time complexities and space complexities. So when we're doing like AI stuff, we generally express time complexities in terms of the branching factor and depth rather than the number of nodes. Which is pretty cool. But yeah, those are 2 very important things to understand. Let's see what else. Yeah, so the branching factor could be infinite as well. So, like, one node could have, like, an infinite number of children. As an example, you can imagine you're playing some kind of game where, like, you're increasing a counter or something. And you're trying to hit a target number. And you can choose to add any number you want from 1 to infinity. So so that means that each node that you have, like each node being like the specific number of the counter, well, that would include multiple, like every node would have infinite number of tokens, but you can choose because there's infinite number of options that you can add to your counter. Right, so that's an example of something with infinite branching factor. Although we're gonna pretend like our branching factor is finite for the demonstration with like BFS and BFS. And also keep in mind that the edges in our tree are defined by the transition function. So if like state A transition to state B, then there's an edge, like a forward. Yeah, so, and important thing to note is that these edges can potentially have weights. You can add costs to your edges in order to kind of like penalize taking like a specific option. might be useful sometimes. Oh my god, fuck this. Okay, anyways. So we're gonna start by talking about DFS, using DFS algorithm to kind of try to solve this problem of state-space search. So, when we do standard state-space search, one term that comes up quite a lot is the frontier. And the frontier is pretty much, it's like our progress meter for our search. So it tells us which nodes we want to check next. So it holds on to a list of nodes that we have not been, that we like want to go to, but we have not visited yet. So for example, in our DFS, that's kind of like, oh my, yeah. So like think of like your BFS. You store all your nodes in like a queue, right? And that queue tells you which node to visit next. Yeah. So that queue is the frontier for a BFS. And so similar to how the frontier for a BFS is a queue, the frontier for a DFS is a stack. Okay. Yeah. So the DFS uses a stack as queue, or sorry, wait. It uses the stack as the frontier because if you think about it. Oh my god, I cannot. Not while I'm talking, at least. But, okay. Think about it. When you do DFS, out of all the nodes that you visited, what happened to my... Why did my OSU just randomly close? Oh, okay. Bro, I cannot believe that just happened to me, bro. Are you for real? Okay. Sure thing. Close my OSU. I don't even want to play that song. Anyways, where was I? DFS. Oh yeah, so like if you think about like a DFS, and you want to think about which node you want to visit, you always visit the one that you visited the most recently. And the property of stacks is that you always access the element that you put in last. Like in topic. It's last in, first out. Last in, first out. That's that. And it matches pretty well with our idea of DFS. So that's why we use stack to implement the frontier for DFS. And then, you know, the DFS runs, and then if it finds your goal state, you know, if you find your goal state, then you win, right? But, you know, there are many different ways of evaluating the worth of an algorithm. Mainly, there are 4 things that we talk about. So, you have, you know, the obvious ones, the leak code ones, time complexity and space complexity. And then you also have the actual correctness. So, does it give you a solution? Like if there does exist an optimal solution, or sorry, if there does exist a path to the goal state, will your algorithm find it? And secondly, will it find the best one? That is, the path with the lowest cost. Remember, you can add a cost to your edges. So, can your algorithm find the path with the lowest cost? a guarantee for that to happen. And it turns out that DFS is pretty bad. So, let's talk about time complexity and space complexity first of all. So, let's say, okay, first of all, let's start off with a finite tree. So, let's say that this finite tree has a height of d. Oh my god, my fingers. Has a height of d and a branching factor of b. And the number of nodes in this tree is gonna be b to the d. So then you can expect your DFS to run worst case b to the d. You know, just by like virtue of exploring every single node before exploring the gold node last, right? Which can happen, right? You can make it happen. So worst case time complexity is b to the d, exponential, pretty much exponential in d, the height of your solution, pretty much. Okay. Then let's talk about space complexity. So this one is a little bit interesting, and it does require a little bit of imagination. So picture a binary tree, okay? Every node has two children, left child and a right child. Okay, I'm too tired for this shit. Okay, so you have a binary tree, and pretty much every node has two children. And let's say you want to run a DFS on this. Let's not worry about what the goal states are for now, but let's say that a DFS always picks the left child first. Okay, so now, what is it? Now we're gonna think about how many nodes it stores in our frontier, because if we're trying to calculate the space complexity, then we need to figure out what it's storing. Well, the only thing that it's gonna be storing is our frontier list, and we're gonna forget about the visitor array. Usually, when you do DFS, you would have like some kind of like visitation array to determine which place you've been to, but we're not gonna do that here. I guess, yeah, you'll see one. But anyway, so essentially, in order to figure out our space complexity, we should analyze how much our frontier has to store. And a really nice way of doing this is to figure out how many nodes the frontier is storing from each deck. So let's think about like our DFS having like fully run, like through like one path, so, like went all the way down to the left, and then it stops. Like there's no more path. Okay. Now let's think about how many nodes are in our frontier now. So starting at the root node, we explored the left child, so the left child is not in our frontier anymore. The right child is unexplored, but we've seen it before. So our right child is in our frontier. That's one node at the first level. At the second level, we visited the left child, and we went down. We explored the left child and the left child, and then that just leaves the right child of the left child of the root node, and then that's just plus one node in the frontier. And so we can continue this pattern down further and further. And we'll come to realize that at every level, we're only storing, we're only keeping one node in the frontier. Right? So every level, at every depth, you're only storing one node. Specifically, it's gonna be your, if we were to generalize this, it's your branching factor minus 1 on average. Right? Because you have B, let's say you have B children. You go down one child, but then you still have to store the other B minus 1. So that means that every depth you store B minus 1, and you traverse up to a depth of D. So in total, that is a space complexity of O of ED. So before, we were actually, our time complexity was exponential in D. But now, it's linear. Which is cool. And now we can revisit our idea of the visitation array, where we store all the things that we've been to. Well, the thing is that if we store all the things that we've been to, well, in the worst case, we've been to every node, so we store every single node. Okay, and then if we did that, then that would give us again, exponential space complexity. And we'll see that one of the advantages of running a DFS is that it has very efficient. It's very efficient in space. Right? Like you have exponential time complexity, but only linear space complexity. It's pretty insane. Right? So we don't actually want this visitation. And actually it ends up not mattering anyway. Because we're gonna talk about kind of fuck. Yeah, so the other two things that we're gonna talk about is does DFS always find a solution? And if it does find a solution, is it always optimal? And the answer to that is no and no. So, A, it will not always find a solution, and B, that solution is not guaranteed. Like, if it does find one, it's not guaranteed to be optimal. And I think the optimality one is quite clear. Like, you could have like 2 nodes, like two gold nodes, and you could traverse down like one of them and then find the one that's on a longer path just because you randomly chose that. Like, that can happen. Yeah, and then the original one was, does it ever find a solution? This one's an interesting one because it does find a solution if have a finite state space, but there are cases where we work with infinite state spaces, and also since we removed our visitation array, we can actually get caught in a cycle. And so if we get caught in a cycle, then we're likely not gonna find a solution. But okay, even if we don't get caught in a cycle, we can have it. Remember, our state space is infinite, so we can just get stuck down the wrong path and then just traverse it forever. And then in that case, we would also not be able to find it. So from the looks of it, DFS is really bad. Cannot find a solution sometimes and not find a optimal solution sometimes, which are both pretty big things that you want in an algorithm, right? So now we're gonna move on to an improvement, arguably, to the DFS, which is the BFS. What happens? So the BFS is almost the same as the DFS, except that instead of using a stat to implement your frontier, you use a cube. So whatever got put in first will be used first in, first out. Oh my god, bro. So, we're not gonna dive too deep into it, but let's talk about correctness now. So, is DFS always guaranteed to find a solution? Well, this is, yes, actually. It is guaranteed to find a solution. It is guaranteed to find a solution if your branching factor is on it. If you have a finite branching factor, then your DFS will find a solution. Why? Because so BFS, as an algorithm, it searches all the nodes at a specific depth first, and then moves on to the next depth. So then if you have a finite branching factor, every depth takes you a finite number of times, because there's finite number of nodes at that depth. So if you have a solution that's at depth D, then you finish all the depths, like you finish searching all the depths, like from 1 to like -1. It actually terminates, and then you find all the nodes at depth D, which again terminates. So you will end up finding a solution, given that you have finite branching factor. So now, does it find optimal? Okay, this one's interesting because it finds the optimal solution. My accuracy is so much. It finds the optimal solution if your edges have the same cost, right? Because in that world, the shortest path is equal to the lowest cost. So BFS always finds the shortest path to some kind of solution. So it finds the solution that takes the fastest time to get to, but that also turns out to be the most efficient with all your edge costs. But this is not necessarily the case if you have if your edge weights are different. So like you can have like a solution that's like really like the depth of it is not that far, but it has a really high cost, and then there's another solution hidden like really far down, but like every like the cost is really low. Like by weighting the edges differently. So yeah, BFS is not always guaranteed to give you optimal solutions, which again is I don't like to see that on your nose. Bro, I don't know why, but my nose has been so itchy. It's like I don't even know, man. Like maybe it's because I fucking breathe, and like my nose hairs are tickling my nose. I don't know. But okay, anyways. So yeah. So, to summarize, BFS always finds a solution if you have a finite branching factor, and it finds an optimal solution if your edge weights are all the same. Now let's talk about time complexity and space complexity. So time complexity is the same as DFS. Worst case, you search all the nodes, but in a finite graph. Yeah, so you search all the nodes of a graph, right? B to the D. And that's space complexity. So let's kind of use that idea that we had from the DFS. We want to figure out how many nodes the frontier is storing from each depth. So like when we're on our first iteration, we're trying to explore all the nodes that are distance of 1 away from our root node. And so if we were to use our binary tree example again, that would be 4. Or sorry, what the fuck am I saying? It would be 2 nodes. You would have 2 nodes in your frontier. Okay. Then if you're trying to find all the ones at distance 2, then it's just everything on the second level. So that's 4. And then you continue, you get 8, and if you go further, you get 16. So it seems that the number of nodes we have to store doubles each time we increase our depth with the BFS. And so yeah, this actually means that our space complexity for a DFS for a BFS is exponential. B to the D. So even though BFS can find you a solution, like pretty much like under specific conditions, problem is that it has really bad space complexity, and that is a turnoff. And so now I introduce you the solution. So pretty much, this method gives you the same like correctness conditions as the BFS. So it can find the solution if your branching factor is finite, and it also finds the optimal one if all your edge costs are the same. And it also has a linear space complexity like the DFS. So we're basically combining like the best of both worlds. And to do that, we use a mix of both algorithms, mainly DFS. So what's the issue with DFS? The issue with DFS is that it can get stuck down one path. So what we do is we simply prevent it. Oh, this really wants me to like, what you do is you have to prevent it from getting stuck down one path. And so what you do is you put a bound on the DFS traversal. So you can only, like, let's say for your DFS, you limit it to like a depth of like 100, say. So that means that it can only traverse 100 nodes before it gets forced to stop. And that removes the issue of not getting stuck down a path, but now we might not be able to find a solution, right? Because like, what if you have what if your only solution is at a depth of like 101? Well, that's no problem, because if we find nothing at depth 100, then we can just do the exact same thing, but just use the depth of 101. And that's the idea behind this new algorithm. And there's a really great name for it. It's just called iterative deepening. So they're like iterating deeper and deeper. So at every iteration, here's how it works. You're gonna start by storing all the nodes at depth 1 using DFS. So use DFS, but make it so that you can only explore one node before quitting. And then if you haven't found a solution yet, then you increase your bound. So your DFS can now go 2 nodes without switching. You have to go 2 nodes without quitting. And then if you can't find another thing again, then you go 3 nodes. And then 4 nodes. And then 5 nodes. And then again and again. And now, for the same reasons as the BFS, it finds a solution if your branching factor is finite. And yo, what am I doing, bro? Holy. And it also finds an optimal solution if all your edge costs are the same. But now, if we think about the efficiency side of things, it doesn't really seem that great, right? Because we're repeating a lot of work. Which seems kind of fast. But actually, it's fine. Let's talk about the space complexity first. So since we're using a BFS, or sorry, we're using a DFS in the algorithm, our space complexity doesn't change from linear. So it has the same space complexity as DFS. Since we're using the DFS algorithm, which makes sense. Now what about our time complexity? Well, we have to do... like if we have a solution at depth D, then we would have to do our iterative deepening thing times, right? And on iteration I, this has a runtime of b to the I. And then b to the I, and then do that from 1 to d. But then that's pretty much just a geometric series, right? Like you do, it's like b to the 0 plus b to the 1 plus b to the 2, and then so that's literally just you can use the geometric series formula, and you get that the total time complexity is b to the b plus 1 minus 1 divided by b minus 1. And so, realistically, if you compare that to our original time complexity of b to the d, it actually just differs by a constant factor of b over b minus 1, which is crazy, right? It's insane. Right? So you do all this extra work, but then you only get it only gets worse by a constant factor, and that constant factor is really close to 1 if you have a large branching factor. Remember, our constant factor was b over b minus 1. This song's too hard. It was b over b minus 1. B over b minus 1. I think I've said that 5 times. So yeah, your time complexity doesn't change that much by a constant factor, so it's still exponential. You don't get super exponential. Yeah, so in summary, we have state space search where we're trying to find a goal, some kind of problem that we have, and we're going to do it using search algorithms. The methods that we proposed were DFS and BFS. DFS was efficient in space, but it was not guaranteed to find us a solution. BFS, on the other hand, was pretty good at finding a solution, even though it's not optimal. But its space complexity was really bad, and then we kind of made like we had a workaround with iterative deepening, which pretty much allows us to find a solution like the BFS, while also maintaining our linear. Oh my god, maintaining our linear space complexity, um, while doing so. And so that is State Space Search Part 1. And then in Part 2, we're going to talk about how to actually find a optimal solution using another kind of algorithm called heuristic search.